and then we put it on the Google Drive. Okay, so you can start now.
Okay. Thank you, Brian, for giving the chance. So today, I think we will spend time to talk about an example of Lefschetz fibration, which is the Milnor fiber of type AM. And the reference for today is mainly these two papers, one by Covalent Seidel, Quivers flow, cohomology, and break group action. And then the other is Seidel Thomas, break group action on derived category of coherent shift. Because this is a mirror symmetry seminar, right? So yeah. Actually, we are looking at a collection of Milnor fiber. So it's actually a Milnor fibration. I will say more about it later. Okay. So maybe I talk about motivation, my motivation on this topic first. But so currently my PhD project is not on this, but on other stuff. It's on some Heisenberg algebra action on Hilbert scheme. But this project, I touch on this project because we learn about the let me write down the so we under Tony we learn about the zigzag algebra. So this is called the zigzag algebra. I won't tell you what is zigzag algebra because we won't use it in today's talk. And feel free to interrupt and ask. And if I can't answer, maybe Brian can help. And yeah, feel free to ask any question. And yeah. So my motivation is we learn about this zigzag algebra, module over this zigzag algebra, and also the bounded derived category of this. Okay, because this is bounded, this is actually the homotopy category. Is same as the homotopy category. Okay, and what interesting about this homotopy category is this homotopy category has a break group action. So you got a break group action here. You also got a break group action here. And this break group action actually categorify the Burrell representation of m+1 punctured disk. Okay, so they in the Covalent Seidel paper, they relate this algebra to the Fukaya category, bounded derived Fukaya category of Milnor fiber, which is the topic of today. Okay, let me denote it as M. Sometimes we write M2N because symplectic manifold is always even dimensional. And this M is just the Milnor fiber. I will, so this is just motivation. I'll give the full definition later. Okay, so maybe I give some, yeah. So this is mirror symmetry motivation. So this is Milnor fiber. Okay, and yeah, so I touch on this project is because there's a faithful break group action on this bounded derived category. Okay, so this also answers some question on the symplectomorphism on this Fukaya category. Okay, and yeah, so maybe I just give you a picture here. So
this Quran of Seidel, is that the equivalence or just there is equivalence of two categories?
Yeah, it is. But you need to consider this algebra as a differential graded first.
Okay, so then this K0, K, what is KB? What is K stand for?
KB is homotopy category. So you have the
Okay.
chain complex and then you quotient out all the homotopy.
And the DB?
DB is you take the projective resolution. You take one
Okay.
chain complex and then all the projective resolution of that chain complex are the same.
Okay, so maybe it's, I'm not. You are not asking you to explain this. Is a reference for this top one?
Yeah, the reference is this coincider.
Coincider. Okay.
Yeah. And okay, yeah. So the mirror symmetry of this story. Okay, wait. Let me back up a bit. So let me write down this.
Because I feel, I mean, I didn't read it. I feel that the top two, I always think they're the same thing. Because
the top two. Oh, this top two. This you mean this top two are the same thing?
Yes.
When
I mean, as I say, I just like my
yeah.
own naive version of this, because you look at algebra, you look at the modular of this algebra, and then you look at the chain complex, DG algebra of the chain complex. And
I'm
the
not
other
sure.
one is the home. Okay, so maybe I didn't know much about this. Okay, so maybe I will look at that.
I'm not sure about different algebra, but for this algebra, when it is bounded, then these two categories are equivalent.
Okay.
Yeah. And then, oh, okay. So what's good about this equivalent is so in symplectic geometry, it's hard to study their group action. So they study it in this topological setting. Where this topological setting, we can study from this algebra. So there's this commutative diagram. So because this is hard to study, this is easy to study. Okay. So once we establish this is faithful, then in symplectic case, you also have this faithful. Okay. So where's the mirror symmetry in this story? So the mirror symmetry in this story is you also can associate this algebra to one bounded derived category, which is the bounded derived category of coherent shift. And what surface you need to look at? The surface you need to look at is, so this surface should be first Calabi-Yau, okay, and then it is a smooth quasi-projective surface, and also has a symplectic action on it, which is by the group, the cyclic group. This cyclic group is a finite subgroup in SL2. Okay. Yeah. So somehow they started this is because suppose they assume the conservage mirror symmetry here. So maybe they hope like by studying the break group action, they can guess what's the equivalence they can take between these two surfaces. That's why they come out with this spherical object. Okay, let me write down this. So you have this triangle here. So we have this triangle relating each other. So here we got the Lagrangian sphere. And in algebra case, we have projective module. It's just this algebra is like a path algebra. So when I multiply with this I, it's like this is the constant path at the vertex. But never mind, this is some projective module. So it's algebra times an idempotent. And the spherical object here is some local ring times some tensor with some erect. So these are the spherical object. So they come out with this spherical object to describe these things, these actions. And in today's talk, we will talk about this type A configuration in Milnor fiber of type A. How we get these type A configuration.
So EREP is some group, some representation.
EREP, yeah. EREP is if you consider the representation of EREP is coming from wait, let me see. EREP is coming from the EREP of this group. So you consider the irreduced representation of cyclic group. It's finite. The number of EREP of Z mod Mn is equal to the number of conjugate C classes of Z mod N. So there should be M plus 1. Yeah. So yeah, maybe I talk about like why is it type A. So type A is like if you take, let me call this Li sphere. So AN configuration is like if you take AI intersect with AJ is equal to 1 if I minus J is 1 and 0 if they are distinct.
You mean the 1 point no empty?
Yeah.
Okay.
Yeah. So the picture you should have in mind is like it's like this. So on. Okay. Yep. So this is AN configuration. So we will in a moment we will see how this appear from Milnor fiber.
So N means the number or N plus 1 number of spheres.
M, yeah, right. M,
how many?
M, M of them.
M.
M of them.
But the irreducible, you have M plus 1.
Oh, yeah. Right. Wait, let me think.
Maybe you forget our trivial representation.
Yeah. There's some subtlety here. So do you know about Mackay correspondence?
Maybe heard it or read it a long time ago. I couldn't recall.
Yeah. So M. Okay. There's two maybe a bit confused number here. So M plus 1. My thinking is like this. So M plus 1 is referring to the puncher on the disk. Okay. So you got M plus 1 puncher, and then M is these curve are M.
So this M plus 1 puncture.
M plus 1 puncture, and then M curve. Okay. In this motivation, I will call them spherical object. Later we'll see why these are spherical. Yeah.
Yeah,
Okay.
it's just a convention.
Yeah.
It's often the joke about does natural numbers including zero or not? Something similar.
Yeah, because 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 there are two corresponding linking diagram. So you can think of them as affine. You also can think of them as the normal ADE. So the trivial wrap is like
I see.
become the affine linking diagram. Yeah. Yeah.
Okay.
Yeah. So yeah. Okay. Yeah. So this is the motivation. Any question or not? If not, then we will go to our example. We'll construct this Milnor fibration from the beginning. Okay. So yep. So first of all, this is a classic n-dimensional singularity. Of type AM, which is this equation here. Okay, so if you would do the if you know a bit of algebraic geometry, you can do blow up to this object because it has the singularity on 0. Okay, at 0. So you can do blow ups, and then you can get something called exceptional divisor. And then these exceptional divisor will form CP1, and they will form this kind of configuration, which is also like the AN configuration. You only have intersection between adjacent one, and then you don't intersect with the others. So in symplectic geometry case also, we need non-degenerate critical point. Okay, that's why.
Is that
Okay,
CPN or CP1?
I think CP1. I think
Uh,
CPN or CP1. Maybe.
but your x1 x0 to xn, so it's n plus 1 complex.
Yeah,
It has to
maybe it's
be
CPN.
CPN.
CPN, yeah. Because because last time I only look at 2-dimensional. Yeah, I think CPN, yeah. And yeah, right. Because this is in so this is in C. Wait. So yeah. So yeah. So the domain is from CN plus 1 to C. Yeah, CPN. I think CPN. Yeah. Okay. Yeah. Okay. So because this for this equation, the critical point is is degenerate. So now we have to deform it. So we're in a symplectic geometry. So we need to deform it.
So by the way, go back to the example.
Go
so
back.
that example, the function, because there is xn, n plus 1.
N plus 1.
M plus 1. So it's not m is greater than
M
greater than 1 or can 2?
All the powers.
M is, can you have L1 or maybe?
So sorry, say again.
Is it true that all the powers are 2 except for the last one, which is m plus 1?
Yes.
So can m be 1?
Can n be 1? Yeah, you can.
M be 1.
M, you mean this M?
Yes.
I think so, yeah. This
so
is
so if m is 1, then you only have 1. Well, then you don't need the blow up.
You don't need what?
If
m is 1, okay, let's say m is 1, n is 1. So you get G equals G
C2 to C.
Gx G, yeah. You just get this, right? You only got one cylinder, then you got nothing to play around, right? So I think this, yeah. So if you check this at different, I think this thing correspond to this kind of picture. If you take this to be equal to some.
So then again, is how many CPN here? Is the number of is M or maybe?
Oh,
M.
yeah. M.
Yes, M.
Yeah, you should think of this CPM as this curve. So this curve is like you playing around with CPN. When we so right, yeah.
Okay, I just.
You mean these are M of them? Yep. Okay. So, any more question? Okay, and then next one. So
sorry. So
yeah.
the CPN is the blow up thing, right?
Blow out thing, yeah.
The zero divisor thing.
Yep.
Then why there are M copies of CPN? There's only one singularity, right?
Oh, because like this because only one singularity, you keep blowing up. Because when you blow once, you still have the singularity. Like you haven't finished resolving it, so you need to keep resolve M times. Then you get the.
I see.
Yeah, you won't get a singularity. And then you can check their intersection, which is the intersection like this, the type AN configuration. Yeah. Okay. So yeah. Okay. So now.
Maybe the each you blow up. I don't know. Maybe you check reference. If you blow once, maybe the M will decrease by one.
Yeah. You blow once, it decrease once,
and then until you reach to this like a Morse function, all the squares. Then you have only one. Then you have last blow up, just adding one more CPN.
Yeah, right. Yeah, right. You blow out until you don't have the singularity. Checking the Jacobian matrix. Yep. Yeah, right. Yeah, when you check, when you do a blow up, then you check the coordinate, then you will see how they intersect. They intersect at some infinity point and then something like that. Yeah. Okay. Yeah. So in this Seidel-Kovanov case, they have to do this smooth out thing. So which is a linear smooth out. So using they call M+1 parameter deformation. So you should think that they introduce some deformation at the last coordinate. Okay, and then how they smooth it out? So this HW is actually last time I gave this example in the mirror symmetry last semester, but quite briefly, so today maybe talk a bit slower. Okay, and you might wonder how we pick this WM, right? So later we will see how to pick those WM. So now you look at the inverse image of the 0 point. Okay, and then by Milnor, this if you intersect, so Milnor is like intersect like to take the singularity to intersect with a sphere, because they have this thinking that the topology inside this intersection is the same around the singularity. Okay, this is what they did. in the very old days. So you take this inverse image and then you intercept with a sphere. Okay. So this 2n plus 1 is a real dimension, right? Because just now we start with Cn. Okay. And maybe for your intro, so yep. And then yep. And then you can, in this space, the we pick the contact form to be this. Is this a standard contact form on Cn, Brian?
Contact form is on the spheres.
Oh,
It's
fair.
odd dimensional. So if I think that if you D that one, if you D that will be the
area form.
The symplectic form.
Yeah, the symplectic form.
But being contact actually restrict to the boundary.
Okay.
To the sphere 2n plus 1. So that is the contact form on the S2n plus 1.
Oh, okay. But is this the standard contact form they will pick?
Yes, that is, I think so. But that is like you have this complex ball, 2n plus 2 complex ball with exact symplectic form, which is d theta, and the theta restrict to the boundary. We'll have this contact form, which is theta. If you d theta, that's symplectic form, and then you to the power of n, and then wedge theta. You like a theta wedge d theta. D theta is the power of n. That is 2n plus 1 form. That 2n plus 1 form is a volume form on the boundary sphere. Okay. This is the standard one on the spheres.
Okay, so this is the symplectic structure on this HW. And okay.
LCK, do you mean CN?
Which one? Oh, I think
CK,
it's
okay.
I think it's CM. Yeah, n plus 1. Okay. Yeah. So I still haven't tell you how you pick W, but if you pick it quite small and vary it, you still have this property. Maybe I just write in here. And then for sufficiently small W, you still have this property here. So I write 1 is the radius is 1. Okay. Okay. So let us consider a collection of these things. Okay. And then there's a lemma is these things these are smooth family of contact manifold. If you look at the inverse image of your polynomial and intercept with the sphere, radius 1 sphere, and then you restrict the form, and then this collection of HW makes a trivialization. And this is important for it to form a Lefschetz fibration. Okay. And yeah, any question? If no, then let's continue to construct this Milnor fiber. So so now let's say we pick those W such that such that you don't touch any singular point of your fiber. And then we will define our Milnor fiber, which is the intersection of this HW with this closed ball. Okay. So all the symplectic form, contact form are just restriction of the previous one we picked. And so what property does this have? So the thing we pick here is what we call a Milnor fiber. This is over 1W. So this is a Milnor fiber. This is a symplectic manifold. Okay. Okay, so this W, why can we pick this W is like, this is a theorem from Milnor. So Milnor said that exists some small number such that if you pick this W, they intersect transversely. So these are all by Milnor, done by Milnor. Okay, in the singularity points of hypersurface by Milnor in that book. Okay, so this is just one fiber. Okay, so what's the Milnor fibration? Milnor fibration is, you consider a collection of them, which is this. To W. So this is Milnor fibration. And the fiber is the Milnor fiber. Okay.
So in the lemma above, that's actually a fiber bundle, but in the downward this pi, it's not a fiber bundle, it's just a fibration, right?
In the yeah.
Okay.
And yeah, yeah, right. Every fiber in the fibration is a fiber bundle. Is it? Is that right?
No, every fiber bundle is a fibration, but not the inverse is not true.
No, I mean this Milnor fibration is a collection of fiber bundle. Is that right? Because every
you only look at the W. You only look at the W, which is no singular point.
Then we get a fiber bundle since there's no singular point. And but in the downward this pi there is there singular point?
It's restricted to this. It's only looking at.
Yeah, I think there is. If there is, what's the problem?
W, the fiber of E over W. W should be like a regular. Contain no singular point of HW. This is more general than the last time Lefschetz fibration. Lefschetz fibration is only W, like for here you have 2m plus 2, so m plus 1 complex parameter. So this singular point of HW. Singular point, no singular point. Yeah, if no singular point, then this pi would be fibration. Yeah, it's fiber bundle, local trivial fiber bundle. Is a local trivial fiber bundle. The fiber is Milnor fiber, which is symplectic with contact boundary. Dimension. Okay, I think we need to think about this.
What's the problem here?
I mean, the Milnor fibration is different to the Lefschetz fibration. Lefschetz fibration, the Morse function, which is to W. What is map? What is this map W? W. Maybe go back and check. You have Cn plus 1 cross W, but W is inside the B 2m plus 2. And then GWX is 0.
GWX is 0.
GW 0. So it's different if you think compared to Lefschetz fibration. Lefschetz fibration is starting with Cn plus 1 to C.
Cn plus 1
then the here you have
W is also in Cn plus 1.
C2m, m plus 1. Is m plus 1?
And m, yeah. Why I write m here? So these are all m. Sorry.
Oh, okay. You have.
Sorry. Should be m.
M, right? M.
Yeah. Every n should be m.
Really?
Yeah.
But you're starting with.
Oh no. Sorry. Okay, there's two parameter here. So there's two parameter here. So yeah. So there's two. So one is the dimension of this, and then m is the dimension of this. So here m should be n. Sorry. So should be n. Everything is n here. This is following the Cn plus 1 dimension.
No, really? W.
Because W, is it?
W have m plus 1. W is the deformation for the.
Oh, right. Yeah, right. Yeah, right.
W.
Yeah, right. Those are okay. So these
okay,
W.
So your G. Okay, maybe that your GWX is 0. So that imply you look at the first n matrix. So sum over I from 0 to n minus 1, xi square would be minus HW. HWXN, right? Is that relate?
Mm-hmm.
Maybe it is maybe related to Lefschetz fibration, but it's
they call it symplectic fibration.
so I mean so you somehow put the equation. The equation is GWX is 0.
Right.
And then if you look at the GW expression, that essentially like a Morse function, like all these xi square, I from 1 to n minus 1 equals to minus deformation, which is minus HW xn.
Correct.
Now this HW xn, of course, is
some
HWn is polynomial of n plus 1. And so I try to relate to the Lefschetz fibration, but then you have this another parameter. So maybe W is there is a map from W to C, which is that true?
From W to C. W is a tuple. So W is a tuple of W. Sure.
If you fix W, then you have this polynomial of degree n plus 1, and evaluate xn, so that's HW xn. Then W is those points where there's no singularity of HW, no singularity of HW.
So HW is looking at the singularity of this thing. So this is.
Oh, I know. Maybe because as long as you have this polynomial HW xn, right? You have HW xn. So as long as this HW xn is not 0, if that is not 0, and then GWX equal to 0 is not a singular point. Because if HW is not 0, so you have you have the singular point happening whenever you have HW xn equal to 0. That is n plus 1, so zeros of HW.
So let me maybe give one example.
Okay.
So just now you say that the H. Okay, let me give some small dimensional example. So if you consider this this set here. So this set, let's call it Q. If you draw this thing out, this is like two sheet of C1, C1, yeah. I take this picture from the Arnold singularity theory textbook. So this is like you cut off from -1 to 1, and then you join this two sheet. So what you get is something homomorphic to this cylinder. This picture is quite important. This is lower dimensional case. Yeah. So this is when the HN, the HWZ thing is something, some real number, some scalar not equal to 0.
You mean instead of 1, you mean C?
Yeah. But in this case, if I pick C to be 1, then this picture is
Okay.
I mean, if this is not 0, So we write this is, yeah. So this is the case when hash w xn x1 s2, in this case x2 is not zero.
So when hwx2 is not 0, and then that is
example I take when it is 1, then you get this kind of picture. But in, yeah.
So that means this w, this your this little w, big W. You have big W. You have big W. You have big W, which is the no singular fiber. So that is no singular fiber that corresponding to the HWXN, not 0.
Should they be the same thing? Yeah. So if it's not 0, then the polynomial you get is not 0.
Yes, sure. Then this is depend on xn. Depend on xn. This Milnor fibration. Milnor fibration is you take any point in the base. At wm to w0. Those the point HWXN is not 0. Yeah, so E you have two components, X and W.
Okay.
So X should be 2n plus 1, it's not n plus 1, it's n.
You mean you mean which one? The
just on the screen. Now that you have this consider pi E, and you have X component, you have X and W,
right.
And this X should be n plus 1.
Oh, this, okay, yeah, right.
It's n plus 1. And the last coordinate xn is there is a map HW. We apply HW to xn. So okay, as long as it's not 0, then you have this equation GWX equal to 0. But GW equal to 0. Where is the Milnor fiber?
GWS equals 0 is the whole thing. Is this?
Yeah, so
is this thing equals 0?
So that is 0 means the first n term, the square of the equal to minus HWX.
Correct. Correct.
And then the W is where this HWXN is not 0.
Yeah. I think so. Yeah.
Oh, I think that then there is another parameter xn. So the fiber is not just the cylinder; it's a cylinder cross. I think a C. Suppose that HW is not 0 for any xn. So you said that in this example, you just did
this example.
Yeah, in this example, the HWX2 is non-zero. For any x2 or
for any x2.
If you fix W, if you fix W, then this polynomial of degree m plus 1
right
will always have m plus 1 zeros for x. So in this case, your x2 will have m plus 1 zeros.
Correct. M plus 1.
Because Milnor fibration, maybe you need to
Oh, and then one more thing is this circle is the so-called vanishing cycle.
WT.
Or even the HW is 0 at some certain point. The 0 is not critical value since Milnor showed that the preimage of 0 intersect transversally to the S2m+1. So, Brian, do you think that the whether there is singularity is independent of the HW, whether HW is 0? So it can have 0 points, but it cannot be constantly 0.
And then this W set, the set of W, is a subset such that it contains no singular point.
Yeah, but it's not equivalent to whether HW is 0. HW can be 0 at some certain point.
HW equals A. Okay, now. So maybe we will think about let's just probably we'll continue. Actually, we'll already. We will continue next time. Right?
Continue again. Okay.
Yeah. So
maybe next time I talk about more about this example and then see.
Are those reference in Dropbox?
I'm not sure. Are not. I think the Covalent is in the Dropbox, but the Richard Thomas is not. And then this is from Arnold singularity theory.
Okay.
This is a book or this?
Yeah, this is a book. Yeah, there's a book.
A single book or a volume or several volumes?
Yeah, it's actually from several volume, but I found a book on it, so it's called singularity theory.
Okay, if you have a electronic version, put it on Dropbox.
Oh, I put on.
And then next time probably we'll look at this Milnor fibration more closely.
Yeah.
Because somehow try to relate to the Lefschetz fibration. But somehow it is related.
But I saw in the book they actually call it a symplectic fibration. Are they the same thing?
When symplectic fibration means a fibration of fibers are symplectic manifold.
Oh, okay.
Here the Milnor fibers. Here the Milnor fiber. You have this. Everything is in complex. So the